Hey everyone, JD Harwell here, and today I want to talk to you just briefly about the downregulation of opioid receptors. But before we talk about downregulation, I'd like to talk about another downer, and that is the fact that I would not like this video to be used for any other purposes than educational purposes within the course and semester in which it was created. For starters, it's important that we define what downregulation is in the context of this conversation. So, for the purpose of this paper, downregulation is defined as any process that lowers the number of receptors. Any process which lowers the number of receptors is going to be downregulation. Now, the specific receptor that we're talking about is a G-coupled protein receptor, and we all know how those look, so I'll draw one in right here. Now, for the opioid receptors, there are multiple variants. The three that are expressed most in the central nervous system are the mu opioid receptor, the delta opioid receptor, and the kappa opioid receptor. Now, with regards to downregulation, we see it happen most with the delta opioid receptor, and in many places you're going to see it abbreviated as DOR, and you should be able to remember that this one is downregulated the most because you see downregulated, and that makes it pretty easy to remember. So rather than drawing out all of the receptors, I'm just going to put some deltas, since we're talking about the delta variety having this happen the most, but I'm going to just draw in some deltas, and these are going to represent our G-coupled protein receptors. And if this right side represents the normal state of the cell, if this is the normal state of the cell, then when this is activated, when our receptor is activated and a decision is made to undergo endocytosis, the next decision that has to be made is whether or not to recycle that receptor and send it back to the plasma membrane, or to degrade the receptor and send it to the lysosome. If it's degraded, then we end up with what we're going to see filled in here is far fewer receptors in the membrane, and that is downregulation. So one of the ways that we can cause this downregulation is by degrading the receptor within the lysosome. So we're going to activate our G-coupled protein receptor. That's going to cause the conformational change in the heterotrimeric G protein that we're familiar with over here. And we have to just make a decision whether we're going to bring that into the cell via endocytosis or not. If we don't bring it into the cell, then that's never going to be downregulation. If we do bring it into the cell, then we're going to see the invagination, the clathrin-coated pit that we're familiar of, formation of an endosome, and then if we remember from the last unit, the endosome, for endocytosis, the endosomal compartment is the primary sorting center, just like the Golgi is for the secretory pathway. So we're down here and we've got our endosome formed, and we have to decide where that thing is going to go. Now, there is another protein or family of proteins called the G-coupled protein associated sorting proteins. And you don't have to remember that, we just call it GASP. I'll write that down. GASP proteins. So we have the GASP proteins. If it does not come into contact with the GASP proteins, then that boy gets recycled and sent back out to the plasma membrane, where it reinserts, becomes resensitized, and can be reused again. So that is not downregulation. If it did come into contact with GASP, then it is sent to the lysosome for degradation, and hooray, we have our first case of downregulation. That's the first way that we can get fewer receptors within the plasma membrane of a single cell. Now, can we think of another way that we could downregulate the number of receptors? Well, every one of these receptors is a protein, and because we know this is a protein, we also know that it must have been translated on a ribosome. So we're going to have a ribosome. We'll trace this thing back. And if it was translated, something had to be translated. That's the mRNA. And where does the mRNA come from? Well, we remember that's going to come here from our nucleus. So we're going to have a nucleus. And then what we're going to do is we're just going to go ahead and pretend that we're going to pretend this entire thing is our nucleus to give us some room to work. So here's our nucleus. So we know within the nucleus we're going to find the DNA that mRNA came from. I'm not going to waste a lot of time drawing that in. You know what DNA looks like. But that DNA is going to code for the mRNA that then codes for the protein, and that protein is our G-coupled receptor. So what could happen to stop that from being put out there on the plasma membrane? Some of the things we've talked about, and a lot of these epigenetic modifications aren't well known, but histone modification is one that we know pretty well. DNA methylation, nucleosome remodeling. We know all of these things that happen, but we have also identified the gene that creates our receptors. So if we can silence, and this happens, if we silence the gene, the OPRM1 gene, then we also could get some downregulation. And so that's the two ways that I found that we can downregulate. And finally, I want to leave you all with a parting important question. What's the difference? What's the difference between a dog and a marine biologist? Well, one wags a tail and the other tags a whale. Thank you so much. I hope you learned a little bit about downregulation of opioid receptors. Have a great day, everybody.